Merhaba, herkese hoş geldin diyoruz. Bugün Çankaya Üniversitesi İnşaat Mühendisliği bölümünden yardımcı doçent doktor Oğuz Güneş'i konuk ediyoruz. Geldiğiniz için şimdiden çok teşekkürler, katkı verdiğiniz için.
Çok teşekkürler. Bir iki kelime Türkçe'yle başlayıp ondan sonra İngilizce'ye dönmek belki daha mantıklı. İlk öncelikle nazik davetiniz için çok teşekkür ediyorum. Uluslararası Çankaya Üniversitesi'ne yabancı yüzler değil, kendimi evimde hissediyorum, kıyafetimden de gördüğünüz gibi. Bu seminere davetini almaktan özellikle mutlu olma sebebim her zaman için inşaat mühendisleri ve mimarların ve şehir bölge planlamaları birlikte çalışan insanlar ya da meslekler olması gerektiğini düşünmeme rağmen nedense bir türlü fırsat olmuyor. Buna gelenek mi diyelim, kültür mü diyelim, meslekler arası bir çekişme ya da çatışma mı diyelim. Ama şurada bir gerçek ki bu olmadan da olmuyor. Ortaya çıkan ürünler tam olmuyor. Dolayısıyla bizim sizlere, öyle düşünmek istiyoruz ki sizin bizlere ihtiyacınız var. Ve de bu ancak işte popüler bir deyimle 1+1'in 3 ettiği bir deneyim herhalde bu şekilde ancak olabilir. Sıkı sıkıya bizler sizlerin neler yaptığından, neler çalıştığından haberdar olabilirsek, siz de bunun karşılığında bizlerin neler yaptığından haberdar olabilirseniz, ortak noktaların bulunmasının daha kolay olacağını düşünüyorum. Bu açıdan da burada olmaktan özellikle mutluyum. Şimdi, bugün belki beklentileri tam olarak karşılamayabilirim. Çoğunuzun malzeme üzerine bir seminer beklediğinin farkındayım. Fakat Zeynep Hoca ile aramızda şöyle bir konuşma geçti. Yani biz malzeme üzerine işte böyle aktivitelerimiz var ve de bir seminer düşünüyoruz deyince ben de eğer aklınızda bir içerik veya format olarak bir şey varsa ben ona göre bana biraz zaman verin, hazırlanıp geleyim. Yoksa eğer siz neler çalıştığınızdan bizi haberdar edin diyorsanız onu hemen yapabilirim dedim. Ve de ikincisiyle başlayalım diye düşündük daha doğrusu. Şimdi benim işte 94'te ODTÜ'den mezun olmamdan bu yana neler yaptığıma dair bir potpourri mi diyelim, derleme mi diyelim, öyle bir şey sunacağım. Ve de daha sonra da sizlerden başta hocalarım olmak üzere geri bildirim isteyeceğim ki bir sonraki buluşmamız eğer olursa daha şekillendirilmiş ve herkese daha faydalı bir buluşma olsun diye. Okay, this may be a good time to switch to English, and I hope that everybody will be comfortable with it. And if you're not, then I know that's a common problem throughout the institution. That's something we have to work on. So it's a rather provocative type of title for the seminar, A Journey in Search of Impact in Materials and Structures Research. You're mostly undergrads, I assume. And when you're an undergrad, like I was once upon a time, people tend to think more idealistic. You know, I still am in a way. That we want to do good things for ourselves, for our family, and for our country, wherever we are. And that was my idea. But throughout the years, my idealism was tested a number of times. And but I would like to think that despite the sways from the right path, despite the zigzags, I'm still trying to make progress in the right direction. And this journey is something I would like to share with you and see if you can relate to it. Let's start with a problem definition. For us civil engineers, there are a number of challenges. Some of them are existing, some of them are ahead of us. And it is not without a doubt that the civil infrastructure systems are the most valuable and most expensive assets in any country. In the U.S., this was measured about $20 trillion. In Turkey, of course, we don't have specific metrics for these, but it is safe to say that it's a big amount. And the current condition of the civil infrastructure systems, if you go outside and take a look around, you can easily see that it's not in its best shape. And obviously, since we are a developing country, we have many lessons to learn from the developed countries and many lessons to teach to underdeveloped countries about developing a civil infrastructure system. And these may be technical, economical, ecological, and social issues that are equally perhaps important in regards to setting up or developing your infrastructure. And for future, we have the emphasis on sustainability of infrastructure. So we want to go greener. We want to build more durable infrastructures that are better looking and that require not much maintenance, if you wish, or sustainable in the long run. And here is an example. It's there because it was easily accessible. The American Society of Civil Engineers does these surveys every 4 years. And as you can see, the infrastructure in the U.S. in 2001 was D+, the overall grade, or the components of the civil infrastructure systems. This is, as you know, is not a good grade. And the amount of investment needed in the next 5 years to bring it to acceptable levels was, in 2001, $1.3 trillion. 2005, the grade went down to D, and the investment need went up to $1.6 trillion, and $2.2 trillion in 2009. One of these days, the new one will come out, and you can be sure, rest assured, that the amount investment need will go up. So not only we need to cope with the existing problems in our infrastructure, we have to come up with more efficient, smarter ways to build better infrastructures so that we can cope with the problems. As you can see, the problems are growing at a rate faster than we can deal with them. And that is a very important problem throughout the world. So the word crisis in Chinese is composed of 2 parts. And this was coined, first made famous by the late American President JFK in one of his famous speeches. And it is Weiji, one part is danger and the other part is opportunity. And both of these are stimulants of research. On one part, the danger is that we have to restore and upgrade performance lives of existing infrastructure components. That's our problem with the existing infrastructure. And the opportunity is we are encouraged, at least, to develop new materials and methods to build more durable and sustainable infrastructure components. And material science and engineering research plays a pivotal role in these. So, personally, my quest is to, based on material science and engineering, and of course, coupled with this, the mechanics of materials and structural mechanics, do high impact research in the areas, in the surrounding areas. And these areas can be summarized as deterioration of construction materials, condition assessment technologies, advanced materials in infrastructure applications, service life prediction and extension, structural strengthening and renewal, natural hazards mitigation, and failure investigation of structural systems. So as you can see, this is a pretty broad area of research. And if you go this wide, chances are you cannot go too deep. That's why when people ask me, what's your profession or what's your specialty, I say I don't have one. Because I search for high impact problems. And when I find a problem, I study the problem, learn what needs to be learned, and try to solve it in the best way that I can. So that means and when you search for problems rather than establishing a specialty area, then things tend to be a bit more difficult, tend to take a bit more time. But if you find the solution, that will be a high impact finding, that's for sure. So it may be a bit unusual and an unorthodox way of doing research, but personally that's what I like. So condition assessment, what does this mean? It can be through destructive testing. As you can see, there's this urban transformation, is it? The English translation, urban transformation. Yeah, the kentsel dönüşüm is a law that is in practice for some time now. And we have huge problems about the condition assessment of existing infrastructure, existing building infrastructure, especially the existing buildings, the seismic condition of these or seismic performance. And we can either go take samples from the buildings and test them, that would be the destructive means, or we can try to come up with non-destructive means, such as using electromagnetics, which includes visual inspection, acoustic, mechanical, chemical, electrochemical. These are the indirect ways to get some information about the current status or the condition of the building. So obviously, if you can have a reliable method, this is preferable. And for this, you can use a number of things. This is the electromagnetic spectrum at the top and the acoustic spectrum at the bottom. And you can see the different components of the spectra. And you can use many of these to get information about materials or structures. And examples, this is a building, for example, the exterior cladding. You don't know what the condition is, but if you look at it with an infrared camera, you can easily detect if there is debonding or what is the status. And on the right-hand side, there is the radar, the microwave radar, and you can travel at the speed of traffic and get information about the subsurface of an asphalt layer. And these are very quick, efficient ways of doing condition assessment using some advanced technologies. So when for my graduate studies, I went to MIT, and being at MIT, you tend to think that you're the top guy in the world, and you're here to do cutting-edge research and cure cancer if possible, things like that. And one of the topics that I came across with was using microwaves to image inside concrete, to see inside concrete. And for this, I took the simulation approach, where there was a tool at MIT, and this is what happens. There's an incident wave, and this is a scatter. It's a target. What happens is when it hits the target, some of it gets reflected, some of it gets refracted, and some of it goes through it. And you can use this information. For example, the forward problem would be, okay, I have a defined target, and if I hit this with a microwave pulse wave, for example, then what will be the response? And that will be the forward problem. The inverse problem is more difficult when you don't know anything, about the target, but just looking at the response, the scatter, you need to determine what the target looks like, what's inside of it. So for this, I won't go into the technical mumbo jumbo, but there's the computational and there's the imaging. Here it is. This is the simulation. This is a concrete cylinder, for example, that is hit with a microwave pulse wave, plane wave, and this is the reflection and transmission. And if you measure it, it looks like this. If you build an image of it, it looks like this. So your initial target was this. If you knew nothing about the target, just looking at the reflected waves, you could say that it looks something like this. Is it good? Well, it has, it depends on what accuracy you're looking at. It is a trial that shows you the limitations of the methodology and the techniques that you use. When there is a rebar, when there's a reinforcement inside of it, it gets more difficult, and you hit the limitations of the methodologies that you use. So the success of it is debatable, but there's no doubt that it's an advanced topic, where if you invest enough time and energy into it, you can come up with an efficient way of determining the condition of materials and structures. Here's another example. This is a steel bridge, railroad bridge, and there are cracks on it. So how do you determine if the cracks are growing, or if it's important, or better yet, if it's dangerous? And another way of doing it is ultrasound. There's something called acoustic emissions. When a crack propagates, it makes a little sound. And if you can catch that sound, looking at as you can see here, we have the crack, and there is a hole drilled at the tip of the crack, and around them there are the transducers that measure these sound waves generated by the crack propagation. So as the train goes over it, there is a trigger system that starts taking time, and you eliminate the structural noise and concentrate on the stress waves or sound that is generated by crack propagation. And by counting the cracks, you try to determine, develop an index that shows at what level is the structural reliability, and at what level is it becoming dangerous for people to travel on. So these are condition assessment technologies, and these are more suitable for MIT people. When you talk to these people, they say, "Oh, we don't deal with today's problems. We deal with 20 years ahead's problems. So today is not our concern." But as I was doing this, it was 1999, and there was these 2 earthquakes in Turkey. So I remember I was in Boston, and I'm trying to, get information about the earthquake. Nothing works, obviously. The internet is not as it is today. So it is quite difficult. And it was a major disaster. And so I can get no information about my country. So I sat down, and from the images that I could collect from the internet, I prepared this brochure. And we set up a table at the main entrance of MIT, and we said, "We need your help, give us money." And I think we collected about $2,500, $2,500, and they liked the poster, and they went around Boston, and about $100,000. Obviously, now think about it, you're from Turkey, you graduated at the top of this prestigious, so-called prestigious university, and you're doing high-end, cutting-edge research, and all that you can do about your country, about a disaster, is set up a table and ask for money from people. That's pretty humbling. This is, ego-bursting kind of experience. So I said, I'm working on wrong topics. I should deal more with what is needed. And I searched into ways of dealing with seismic retrofitting, seismic improvement of existing structures. So, and the different parts of it is seismic modeling. So this is the earthquake waves. It is generated at the bedrock. It travels to where your structures are, and then goes through the soil, and it arrives at your structure, and you have to determine if it is in good condition or not. And this is the model of a structure as we civil engineers do. It's pretty meaningless for architects, and rightly so. The vulnerability analysis shows that if it's a weaker construction, it gets damaged or collapsed under even moderate earthquakes. If it's a strong structure, then only strong earthquakes can damage this. So what you do is you develop the model, and this is when you apply the load, this is the distribution of damage in the building. These are the color-coded damage levels, and this is the capacity, that's the demand. If you get the intersection, that's your performance. If you have an intersection, that means it is a valid performance level, so it's good. If you do not have an intersection, that's pretty bad. Okay, so how do we cure this? And when I looked at the methods, there are the conventional techniques. There are jacketing of columns, the so-called. You add to the existing structural members of buildings, enlargement of walls, addition of new shear walls. Shear walls is what protects, gives additional shear resistance of a building. And innovative materials and techniques, these are FRP materials, fiber reinforced plastics, a pretty important class of materials. that is up and coming, and the supplemental energy dissipation and structural control, these are devices, specialty devices, that can be used in buildings for seismic protection. And those were base isolation, supplemental energy dissipation, active structures, and semi-active structures. So, I learned about these, and I'm eager to go back to Turkey and apply these on site. So I came back to, and these are the conceptual illustrations of the seismic control and dissipation devices. This is what it looks like, and the damper, just like the shock absorbers in your cars. We use them in buildings too. And these are active control devices. That's John Hancock Building in Boston. Specialty devices that you tune to resist the earthquake. And there are some active ones that calculate the vibration, sense the vibration, and counteract to the vibration characteristics. I learned about these, and I have to go back to Istanbul, to Turkey, Istanbul specifically, and apply these. So I came back to Istanbul. I set up a company while at the same time doing my PhD, and I started doing retrofitting work. This is if you're familiar with Istanbul, this is in Bebek, the faculty housing for Robert College. It's right on the Bosphorus. It's a very there are strict regulations about it, and this is the model of the building. And we added several shear walls, and this is the application that we did. That is a shear wall up there. These are additional foundations, and columns are enlarged. As you can see, they are in pretty bad shape, and there's then some additional structural elements. And these were all done without interfering with the front view of the building, because it's the Bosphorus, and you know there are very strict conservation laws, and all that thing was behind the scenes taking place inside the building. And this was completed within 3 months while the school was in a vacation, summer vacation. This is a large industrial building in the Organize Sanayi Bölgesi, Dudullu. And that is about more than 20,000 square meters. And this is the inside of the building. It is a pretty dumb designed building. And I will show you why. As you can see, the main beams or girders. I mean, you know, the definition of a beam is that its aspect ratio is if its width is 1, its height is about 2.5, 2, 3, 2.5. That is the definition of a beam. But these beams are 1 meter wide by 1 meter high. So that is one of the most ineffective ways of designing a beam, because when you make the span 22 meters long, the beam cannot carry itself. It gets too heavy to carry itself. So there was a huge problem, and it gets pretty ugly looking too. And this is how we retrofitted it. We first built shear walls around those very large columns. This is some of the reinforcement, and we added steel reinforcement to the beams. These are pictures from application. As you can see, it is pretty dense reinforcement, and this is in order not to add more weight to the building. This is the reinforcement, and these are steel plates to keep it light. And these are pictures of application. And more buildings inside in Istanbul. I did a pretty high number of condition assessment or seismic performance evaluation. And this is one that at the time, this is 2000 to 2003, the performance-based evaluation and retrofitting was not known in Turkey. Now it is, after 10 years. So, but we did, the problem was, when you have your building checked, they say about, okay, 50 of your beams and 30 of your columns are substandard. So what does that mean? We don't know, but they're substandard. As the building occupant, you want to know, okay, am I under risk? Is this building going to collapse under a seismic event? We don't know. It's just we know that so many of your buildings members are substandard. So this performance-based evaluation gives you, through this performance measure that if your building's performance satisfactory or not. So in those days, this was a novelty that we were able to say, okay, so many of your columns and beams are substandard, but you're under no risk or limited risk or high risk. And that meant a lot more for the building owners. And this might be interesting for you. These are the Robert College school buildings. Of course, they have historic value, and they are in the second-degree seismic zone. And they came and they asked us to perform the seismic evaluation. The structural design of the buildings is quite interesting. In the inside, it is steel frames. It's a steel floor, frame system for resisting the gravity loading. And at the perimeter of the buildings, around the perimeter of the buildings, there are thick concrete walls, but they have no reinforcement in them. Plain concrete walls to resist the earthquake loads. So we did the analysis, and this is what it looks like. You get the elastic stresses, or stresses after an elastic analysis. Now it is quite subjective. You know that when it comes to this yellow color, concrete cracking starts. But when you look at this, is this dangerous or not so dangerous? That's a subjective call because you cannot tell much. So we said, okay, we have to retrofit this building. Now, how do you retrofit a historical building without interfering greatly with its architectural character, historical character? And we studied a number of methodologies. One of them is center coring, going through from the roof down to the subsurface and anchoring the building and putting it under compression. What else? Base isolation, putting isolators in underneath the building so that when an earthquake comes, it's not damaged. What else? The FRPs, you cover the building with these materials, and since they have an architectural value, not the best way. So we thought it was an innovative idea. Let's say, we said, change the window frames with structural steel. They have the windows, so we will change them with structural U-shapes. I have a problem with it. U-shapes, and will make the building not feel these openings, because the problems are because of these openings. And there are the ways, the base isolation was way too expensive for this. And we implemented the analysis, it looked fine, and we did the retrofit application. And this is what it looks like. So that is after the building is retrofitted. And then, as an architect, you may, I don't know what you think. It's, we have interfered with the architectural character of the building, but not in a major way. And this was all done within the summer vacation as required by the client. So you can say that it is a good application. Well, there's one problem though. This is structurally effective, that's for sure. These are the structural steel window frames. These are the steel plates. They are all tied. Now it's a safe building, for sure. But failure has its types. Although this was structurally a successful application, from functional use perspective, it wasn't as much successful. Why? Because, as you can see, these window frames are surrounding the window, surrounding the wall, so it is in contact with the exterior and interior of the building. And later on, as they started using it, they said it gets too cold. The students sitting right next to the window cannot get warm because that steel takes the cold from the outside and brings it inside. So that gets you thinking. There are many levels to doing design. You can think that, okay, structurally I took care of the building, but from functional perspective, it is sort of a failure. One has to think about, okay, this is cold, that's warm, this is a pretty conductive material. It will affect whoever is next to the next to the window. That's an interesting point, I thought. Now, coming to the... Coming to the important building, and this is the main building of Robert College, and it is, you know, as an engineer, the design of this building fascinates me, and as architects, it should fascinate you more. Because if you look at the frame system of this building, as you can see, these columns are going from the base up to the 3rd floor, and on the 3rd floor, there's this large opening that there are no columns. And as here, to have this large opening here, they hang the 3rd and 4th floors up to the roof trusses. So these 2 floors are carried by the trusses on the roof, and what they do is, they take the load, from the floors, they take it to the outer walls, and those outer walls take it back to the foundation. And this is done about 100 years ago, when there's absolutely no computers, I don't know, maybe slide rules, maybe not even so, I don't know. And that design, you have to be a pretty bold designer to come up with such a brave design, I should say. So we looked at this. Of course, we have all the computational tools and so, and that's the stress plot. And 5 expert teams looked at these stress plots, and each team had a university professor in them, and none of them agreed with each other. And the possible cost of retrofitting ranged from $500,000, which was my cost, to $5 million. So that, you know, that doesn't give you much confidence about the engineering business. So that obviously shows us that we need some more reliable tools. The reason is, I have these stresses, but this is due to elastic analysis. Once the concrete cracks, the system is not the initial system anymore. So how do you deal with that? When does the building collapse? That's the question that everybody is looking for. When does it collapse? In a 7 earthquake, will this building collapse or stand? But you cannot give that answer with this kind of analysis. So while I was doing this, I saw that my PhD is going nowhere if I work this hard. So I decided to go back to MIT and finish my PhD. I was forced to do it. And I had problems with the business too, because at that time the code basis was not there, and the market, perhaps it's a bit better these days, but it was a mess. Anyway, I went back. Since you are architects, I tried to include some, you know, nice pictures. That's the Boston skyline. That's the MIT campus. And this is the Stada Center by Frank Gehry. I'm sure you know him better than I do. And the rumor goes, I don't have a piece of paper, that was the pitching meeting with Frank Gehry. And the MIT people are sitting across the table, Frank Gehry on this side. Okay, what do you envision for the building? And he goes, he takes a piece of paper, it's going to look like this. I guess he was right. And the one on the right is one by Stephen Hall, and that is like a more porous membrane type of structure. By the way, the one on the left cost $300 million. And after $300 million, when it was in service, the roof leaked. It happens. It happens. And this looked like Lego, so it's a very interesting building. It's a dorm building. Okay, so I came back to MIT and I'm searching for problems. Now I know the solution. I have experience searching for problems. And this is an interesting graphic that I like showing. Done by Professor Ashby at Cambridge University in the UK. And this shows the relative importance of materials throughout the history. At initial times, at the beginning of, well, not the beginning, but as early as 10,000 BC, the polymers, elastomers, the organic types of these materials, wood, skins, fibers, were the main materials, and people, built with these. And there was also stone, flint, pottery, glass that they used as building materials. Now, with technology, as you can see, there was the cast iron, rubber, cement, refractories, Portland cement, just towards 1900s, and the 20th century was said to be the century of metals. But as you can see, as we now towards the 21st century, the use and importance of metals is decreasing, and plastics and composites are growing. So there's a somewhat strong consensus that the 21st century will be the age of composites, as it was the age of metals in the last century. So with this, when you combine the materials, the existing class of materials, metals, ceramics, glasses, elastomers, and polymers, by combining these, you can obtain better properties out of these composite materials than the individual materials can display. And the structural use of this is FRP, fiber reinforced plastics. This is very thin fibers embedded in polymer matrices. And by this, the main load-carrying elements are the fibers. The matrices hold them together, protect them from the environment, keep them aligned, etc. And you get very favorable properties. And these are already deep in the applications of civil engineering. Here, the pre-stressing tendons made of FRPs, rebars, reinforcements in buildings made of completely FRPs. The whole bridge deck sections, very light, very durable, from completely FRP materials. Bridge spans, complete bridge spans, just hold, since they are very light, just put in place and it's in service. Sheet piles, because in marine environments these have very high durability, so why not? Protruded profiles. You wouldn't think that these are fiber reinforced plastic materials, but they are. And there's a whole footbridge, pedestrian bridge in the UK, made completely of FRPs. And this is a pilot project where a whole building is constructed of FRPs. So I'm telling to my students, I may not see it, well, I probably will, but I may not see it, but you definitely will, in your lifetime, do an FRP design in your profession. So we should start knowing about these types of materials. In structures, well, since these are the early applications, in structures we use them for strengthening of materials. So what we do is we wrap, for example. For flexural resistance, we wrap it on the vertical. For transverse reinforcement, we wrap it around. And this is the strengthening applications. And these are from past applications, wrapping of columns. This is wet layup, this hand layup type. This is for beams, slabs, connections, walls, etc. For improving seismic performance, these materials are used pretty commonly these days, well, in the developed countries, I should say. And these are the types of materials. The good thing about these is you can tailor the properties as you want. You can fix the orientation, or you can stack them with multiple layers and make it a laminate and use it for or adapt it to your purpose. And this is from my PhD. I said, there are a lot of buildings in Turkey that needs to be strengthened, so I should study this. And this is from my laboratory study. I identified the possible failure modes, and I tested these and verified these. I developed an experimental study and showed that the current code is not efficient, it is not conservative, so there's an impact potential here. I showed the different types of failures, the evolution of failure. I classified those failure modes, did a mathematical modeling of it, and I matched it with my experimental, developed a model, quantified the parameters of the model, and came up with this. The current ACI, American Concrete Institute provision, was this straight line, and mine is this, and this is the true curve. So my model performs much better than the existing code. And when I verify this with other experimental data, I get very good results. So in the end, I have a simple, robust, and model that takes into account all relevant properties or parameters, and it gives accurate predictions. When I found this, you would think that, okay, this is a better model, let's adapt it to the code. No, it doesn't happen that way. Then you have to go into the ACI committees, because there are big egos serving on those committees, and you have to fight with them, and you have to get your model accepted, and after that fight, it may find its place in the codes. Well, I'm not willing to do that because it's not a priority research item for Turkey. So I looked into another problem. It worked with concrete, does it work with steel? And steel bridges have these cracks developing in them. I'm sure there are a lot of bridges in Turkey that are developing cracks. Can we repair them? Without a crack, it may not make much sense, but when there is a crack, it extends, if this is the life of the member with a crack, it extends after this composite patching, it extends the life to this. Again, I designed, after some preliminary investigations, I designed this experimental program. I put notches inside steel specimens and patched them with CFRP. And these are the test results. If without the patch, it fails right away. But depending on the size of the patch, as you can see, I can improve the fatigue life. That is, the performance under repeated loading considerably. And the railroad people loved the idea. I presented to them for 4 years, and they said, okay, why do some more tests and do the modeling? And we looked at many things: the surface preparation, how it has to be, the material deterioration under environmental effects, how it affects the performance, corrosion, does it protect or prevent or accelerate the corrosion, etc. And it works out. And this is the non-destructive evaluation, using ultrasound, just like the pregnant women look at their kids. We look at delaminations, debonding underneath these CFRPs. It's the very same technology. Well, a bit more primitive on this side, but it's the same principle. So it works. Again, it is not a priority research item for Turkey. So I finished my PhD, thank God, and right half an hour away from MIT, I found a job. And I find it interesting to say that this is University of Massachusetts Lowell, about half an hour, well, 30 miles from Boston. And when I applied for this position, because I wanted a university around Boston, I love Boston so much, why not? And there were 62 applicants with me, including me. And it took them two weeks to decide that I get the job. Now, when I come back to Turkey, I will tell you another story that contradicts completely with this. I'm coming from Turkey. Language skills questionable, but a graduate of MIT, that's a good reference. But 62 candidates, and they hire you within 2 weeks. So if I were smart, when I started at UMass, I would look at the problems of the US. But since I went to Turkey and saw the problems, I'm still tempted to work on the problems there. So, that subjective thing about deciding on the performance of those Robert College buildings, I developed a much more accurate model, and I got 2 assistants from Turkey, and they modeled this very same buildings using a much more advanced software, nonlinear finite element analysis. And we verified the model. We used complicated material models that takes fracture into account. Fracture is kırılma. It is a very important parameter, and it's not the strength. Dayanım is another thing. Kırılma is a completely different thing. Fatigue is yorulma, just for reference. Okay, and this is now I can see the whole nonlinear curve of a building, and that is a blessing. When you have this, this helps you a lot. And this is, let's see if this will work. Now, here remember that I told you about that third story that was empty of, free of columns? Now, in a linear analysis, it all deforms together. But in a nonlinear analysis, in a few seconds, it will be apparent to you the potential problem with the third floor. Now, concentrate on the third floor. It shows you clearly a weakness on the third floor where you don't have sufficient columns. So that's a pretty reassuring result. And you go back to your analysis and show which ones are sufficient and which ones are not. And thank God, the only one that I retrofitted was not sufficient, which showed that my decision at the time, 5 years ago, was correct. And we modeled the retrofitting. It all worked fine. We have immediate occupancy. Other than that cold issue, it works fine. So what else can we do? And what else we could do was look at collapse of buildings. You know, it's damaging, doing this, deformations and this and that. It's all good. But when does the collapse happen, and how can you simulate that collapse is another challenge that needs some more work by the civil engineers to carry out. Okay, about buildings. If I retrofit them with FRPs, does it work? So another master student looked at that, and we found that it may work, but we need more help. And this is an original design that I developed when I was in the US. Having known, I have retrofitted buildings, and I know that when you retrofit a building, it becomes a mess. You know, initially you say, okay, I don't want people to move out, and I want this to be over in 2 months. But when you go inside the building, everything is redone. So I developed this design to say, okay, I will stay in your flat apartment just 3 days, and I will be out, and it will be as if you're painting the walls. And this is a modular design that makes use of the existing buildings to a large extent. It looks a bit complicated, but it is very straightforward to carry out. A worker can carry upstairs each component of this design easily. So this is something that I'm trying to test, so I come back to Ankara. And I graduated at top of METU. I did my master's and PhD at MIT. I worked 4 years at an American university, and I'm thinking that people will welcome me here. Oh, this is just the guy we're looking for. Pick your institution, will hire you. As it turns out, that's not the case. That was a good education for me. So METU said no. I said why? They said because you're civil engineering major. I said, oh, okay. I said you can do it. I'm the valedictorian here. I said, oh, yes, we can. So I went to Atılım University. Long story short, and at the time, Elazığ earthquake happened. Now, just the thing that I'm looking for. I went to the region, and this is the typical building type, and this is a paper from 1992 about an earthquake happened in the 80s. And these are the damage types of the buildings after this earthquake. Now, if you look at the Elazığ earthquake, which is 1999, okay, this is the 92 paper. That's the 2009. I'm sorry, 2009 damage. That's 92 paper, 2009 damage. 92 paper, 2009 damage. And 92 paper, 2009 damage. In the past 30 years, you see that not much has been achieved in the area. And I searched if people are doing anything about it. Not many is doing anything either. So it's a challenge. So let's take care of it if we can. The problem is, these are far villages in questionable security zones where you don't want your people or workmen to be for an extended period of time. So the the solution, if I can develop one, has to be a quick one. If it's high-tech, that's okay, because high-tech is expensive, but if you do it in a very short amount of time, it can work. So my idea to this would be sprayed composites. And this is composites. You chop, the system chops glass fibers, sprays it on concrete with epoxy, and with sand, and covers the building surface to give it some extra resistance in shear. Is it feasible? Well, we'll see if it works. And to see the buckling of the walls, we are working on developing some anchors.